Okay, so we now learned how to figure out, what is our gas mixture actually made of, and talk about it in terms of mole fractions or mass fractions. But like, how does that connect to our whole ideal gas equation? That was one of the first things we learned about gases, the whole PVD behavior. Well, I'm happy to say it's exactly the same. I'm kidding. That's a lie. It's not exactly the same. We actually have different ways of looking at it. So the first one we have is what's called Dalton's law of additive pressures. It simply says that if I have a gas mixture, the pressure of that gas mixture is equal to the sum of all the individual gases, their pressures, that they would have if they were at the same temperature and volume. So right here, I have gas A and I have gas B. They have the same exact volume that they're going to have when they're mixed together. And they're at the same temperature they're going to be when they're mixed together, and they have a particular pressure. Let's say that the pressure A was 1 and the pressure B was 2. Then what it tells me is that, okay, when I mix them together in that volume, at that temperature, it's going to be pressure A plus pressure B, which is 3. That'll be my pressure. Okay, so that's the first way we can do it. The other way is to do what's called Amagat's law of additive volumes. It says, okay, let's do pretty much the same thing, but this time we're going to have a gas, and we're going to say, okay, gas A and gas B, if you're at the same pressure and temperature, so last time it was volume and temperature, this time it's pressure and temperature, what volume would you take up? And so whatever volume that is, we're going to add that together when we mix it together. So these are two different ways of looking at it. I can do it in terms of volume, I can do it in terms of partial pressures. Okay, so for this, we need to figure out what's my pressure of my mixture or volume of my mixture. Well, it's simply the pressure of the individual components all added together, or the volume of the individual components all added together at that temperature and other property. So PI, that's the component pressure, VI, component volume, and we have our pressure fractions and volume fractions, if I were to divide those. For an ideal gas, both of these give the exact same result, and it's glorious. For actual gases, though, it's not the same. So, other things here. That component volume, okay, right here, as a note, that would be equal to my partial volume if I had an ideal gas. For an ideal, then it's going to be different. And so just showing you once again what that means. So right here, I have oxygen and nitrogen. They're in a mixture. They're currently at a pressure of 100 kilopascals, a temperature of 400 Kelvin. And together, they take up 1 cubic meter. Now, if I were to then somehow split them, so I have all the oxygen and nitrogen separated, still at the same pressure and still at the same temperature because, I just have magical separation powers. What I would find is that the oxygen took up 0.3 meters cubed and the nitrogen took up 0.7 meters cubed. And so that would be how I was figuring out my partial fractions. Now, are these the exact numbers? I don't know. I haven't done the math to see if that would be what it actually come out as. But I'm just showing you here that this is how I would find my component volume. It's this value right here. It's simply the volume when I split it apart, but at the same either pressure or temperature. And for component pressure right here, it'll be for the same volume and temperature. So it just depends on how I'm looking at it. It's easier to show it when I'm doing it based on pressure and temperature because I can more easily divide the volumes. Okay, so with that, some cool things I can learn is if I go back to my ideal gas law, I can rearrange things and I'll realize that, this component pressure and the pressure fraction and the volume fraction, they're equivalent to my mole fraction, which is great. And also they're equivalent to each other. However, this is for ideal gas mixtures, okay? So if I don't have an ideal gas, if there's some sort of issue where it deviates from the ideal gas law, you're going to have more and more errors here. Now, I say partial pressure, and you're like, well, wait a second. Isn't that the pressure fraction or the component pressure? Well, those are not all the same things. This is my pressure fraction. This is my component pressure. My component pressure. And this guy right here, that's my partial pressure. What's the difference? Well, if I'm ideal, my partial pressure and my component pressure are the same. Okay, those are the same. If it's got some sort of compressibility effects, if it's going away from the ideal gas law, it's not going to work, but otherwise it's fine. And this right here is my partial volume, which will be equal to my component volume for an ideal gas. So it just all depends on what you know. If you know the mole fractions and you know your mixture's pressure or your mixture's volume, you can get the partial pressure and the partial volume no matter what, even if it's a real gas and it's deviating from ideal gas law. Okay, right, so one place this really helps us out is for combustion. For combustion, we typically have high temperatures and low densities, which means that we have really good ideal gas behavior. And so we can typically use these relationships when we're analyzing those combustion gases, which is what we want to do because we're all about making power from heat. And for combustion, we usually do that with volumetric analysis. Why volumetric analysis and not mass analysis? Just because it's a little bit easier to do and to measure when I'm dealing with a gas. So you're like, well, why volumetric analysis? What makes it easier? When you're performing it, it just takes a lot less steps than gravimetric analysis. With gravimetric analysis, it just depends what you're dealing with. It's going to take a lot more time. Gravimetric analysis is typically more accurate when you're trying to find these ratios here. But volumetric analysis is fast and it's typically good enough. Okay, it's good enough for what you're trying to do. Think on trying to check your car's exhaust. I don't want to take a whole bunch of time to do that test for every single car in the United States. So I'm going to do a volumetric analysis. I'm doing anything. Okay, so I think, yes, that's it for this time. Next time I'll head into a practice problem. So thanks for watching, and I'll see you all later. Bye-bye.